Welcome to this training session on reinforced concrete beam and column design in space gas. We decided to combine them into one session because they have a number of things in common, including the overall operating procedure and also the concrete manager that lets you manage your beams and columns in one place. So in the column section we're going to be looking at the different types of cross sections that are supported, including voids, load cases, biaxial and uniaxial bending, shear, design actions, column classifications, moment magnification, effective lengths, design priorities, and interaction diagrams. And then in the beam section we'll be looking at the different types of cross sections, the different types of load cases and how they're handled differently, design actions, design priorities, crack control, deflections, moment redistribution, and development lengths. We'll then have a look at the concrete management tool and have a look at things like reports and drawings and importing and exporting and that type of thing. So the model you see on the screen is a typical multi-story building made out of concrete, and in this particular case we've got columns modelled with frame members, and if I zoom in you can see we've got slabs modelled with plate elements. They've got drop panels over the columns. We've got shear walls on a couple of sides. We've got lift cores incorporated into the shear walls, and you've got some voids over here that run through the building. So it's quite an interesting model. The model's been analysed and we can turn on the deflections, just have a look at those. And I'll just turn off the undeformed geometry and then scale it up and down a little bit using holding down the D key and using the mouse wheel. So these deflections here are obviously highly exaggerated, otherwise you'd be a little bit concerned. We'll switch to another load case. So they all look fairly similar because they largely involve gravity loads, even though there are sway loads on this model as well. We've got a minimal set of combination load cases set up that factor the primary loads to ultimate, and we'll use those in the design. And we'll just also have a quick look at the contours in this model, the stress contours. So these are just in the plate elements, and so you can see the colours represent the different stress levels, and they correspond to the legend over here on the right. So I can zoom in. I could also show the values if I wanted to, just by turning on the contour annotation, and then you can move around the model and just see what some of those stresses are. You can show other types of diagrams as well, so I'm just showing the von Mises stresses, but we could also show, let's say, the X direct stresses. And so each different type of contour diagram has different values and different colours. Anyway, I'm getting a little bit sidetracked here, so I'll just turn all that off and zoom back out again. So before we can design our columns, we need to make sure that the cross-section is correct, because the design module won't change the cross-section, it will just add the reinforcement. So let's just have a look at, say, one of these blue columns. So I'll double click on it and then go into the shape builder. And you can see it's just a 500 by 500 square column. And I'm going to leave it at that, but while I'm in here I'll just show you the other types of columns that are supported by space gas. So we can also have circular columns, rectangular, T columns, trapezoidal, cruciform, and one that we just added recently, and it's right over the end here, is what we call a flat oval. So it's like a racetrack shape with two straight sides and then a semicircle on each end. Other shapes can be added, and we can do those fairly quickly, but they're the common ones that most people would want to use. You can also add voids to your cross section simply by adding another shape. So let's say we wanted to have a circular void for a downpipe or something like that. We can just do that. Type in the diameter, and you also need to make it a negative shape by clicking this negative shape box. And then if we click over here, you can now see that it's taken that hole out of the middle. So you can have multiple voids, and the voids can be any shape and located at any position. So I could click on that void and I could drag it around, put it wherever I want, and then I could add other voids that I required as well. In this case, I'm not going to have any voids, so I'm just going to click cancel to get out of there. The next thing I'd probably want to check is that the concrete, or that the columns are made with the correct material and the correct grade of concrete. So in this particular case, I've got 32 MPa concrete, and if that wasn't what I wanted, I could just click this library button here and then go and choose another grade of concrete from the materials library. So I'll leave that as it is as well, and then just hit escape to get out of that member properties dialog. So let's just check one more of these columns. I'll just go in here a little bit deeper and choose one of the ones in here. So I'll double click on that, go back to the shape builder. So this is a slightly bigger column, a 600 by 600, and I'll just leave that one as it is as well. So again, the concrete, or the material, has again been set to concrete, so that's okay. If you wanted to check your whole model, there's a sections and materials panel here, and you can see this one is fairly simple because we've only got two types of columns, and I can click on either of those and you can see they get highlighted when I click on them. And if you want to just check that your structure has got the right material, you can click on the material up there and just double check that everything's okay. When there's only one material like this is a little bit of trivial exercise, but if you've got steel and concrete combined, you may just want to make sure that your materials are as you expected. Now in this particular model, the columns have the same cross section from bottom to top, and so the only thing that can really change is the reinforcement. And if you want the same reinforcement all the way through, then obviously you would only have to design the most critical part of the column, which is normally the part right at the bottom. However, if you wanted to vary your reinforcement up the building, then you would design columns at various locations and get different reinforcement from that. So let's assume that our reinforcement is just constant all the way up in this exercise, just to keep it simple. And I'll choose an internal column here, which is probably quite heavily loaded. So I select the column, right click, and then from this menu here I choose the concrete column design tool. Because I'm using a laptop with a fairly small screen, the menu doesn't fit completely on the screen, so I have to scroll a little bit and then choose it from there. But if you're using a larger screen, then obviously you wouldn't have to scroll like that. So the first thing I'm going to do is just make sure I'm using the right design code, and at the moment we support the Australian code AS3600 and the Indian code IS456. So most of my comments today will be general in nature, but I may at times refer to one or the other codes. Next thing I'll do is just put a label for this column so I can keep track of it. And one of the things you'll probably notice is that without doing much work at all, Space Gas has come up with a design, and you can see the cross section there. You can see the bars summarized here. It's calculated the fitments required, and you can see they're all shown in this longitudinal section here. And that's one of the advantages of the Space Gas design modules over some other programs that require you to specify a trial set of bars before it'll actually come up with any results. So this gives you a very quick and easy starting point. And if you're happy with that design, which is all based on preferences down here that you can set. I'll explain these a little bit later. Then you could just click OK and you'd be done with that one. But I'll just go back in and just explain things in a little bit more detail. So this time, instead of right clicking and choosing from that menu, I'm going to just select the column and then go up here and choose this one here. Just avoids me having to scroll through that menu on my small laptop. So just looking at some of these panels here, we can see the overall column. So I can rotate it and I can zoom and pan, and I'm just using the same controls as I would in the main user interface. So zooming is using the mouse wheel, panning is holding the right mouse button while you drag the mouse, and rotating is holding down the left mouse button while I move the mouse. You can turn things on and off using these buttons here just to get a clearer view. You can also switch to a 2D view that is more like a drawing, so that just shows you that this column is on grid 4. Gives you the length down here, shows you the tie spacings and so forth. Over here we've got the cross section, and again you can zoom in and pan around if you want for a closer look. It's telling us that we've got 4 N36 bars on the top, 4 on the bottom, and then 4 on the sides. So the 4 side ones are these 4. So just remember the sidebar count doesn't include the corner bars. They're included in the top and bottom counts. We've got N12 ties at 540 centers, and our steel percentage is 3.4% of the concrete area. So normally the code lets you stay within a range of 1 to 4% that's the ratio of the steel area to the concrete area, and that's controlled by these settings over here. So at the moment it's complying with the code and forcing the design to stay within the 1 to 4%. Down the bottom here we've got the interaction diagram, and the curve in red just shows the capacity of the column. So this is a plot of the axial capacity versus the moment capacity of the column, and we're looking at the x moments, so they're the moments about the x-axis. The little green dots here, they represent the load cases that we're designing to, and for a pass all of these dots must be within the red envelope. You can see as I move around you get a display, and that's showing the actual values at the cursor location, so that's quite handy if you wanted to have a look at a specific place and find out what the values are. You can also zoom in, so I could just use the mouse wheel to zoom in, and then I can pan if I wanted to have a closer look. Some of the other things here are the purple shaded area, and this is called the confinement region. And the confinement region is an area where confinement to the core is required, and the ties or the fitments have to be designed in accordance with AS 3600 clause 10.7.4. So it's just an area that if a load falls within that area or within that region, then you have to be restraining the longitudinal bars more than if you didn't have a load in that region. If your concrete strength is less than or equal to 50 MPa, then you can design for that. If your concrete strength is greater than 50 MPa, then we treat a load in that confinement region as a failure. So in this case you can see it's added extra ties here to restrain these longitudinal bars, and that's part of the reason, or part of that is because we've got a load, at least one load here that's falling in the confinement region. You sometimes also need extra ties if the longitudinal bars are spaced more than 150 apart, and SpaceGASS takes both of those requirements into account when it's designing the fitments. Some of the other key points down here in the interaction curves are the point labelled ECC, and this is what they call the minimum eccentricity, and the point that coincides with the minimum moment design action, which is usually based on a function of the axial load. So if I just quickly move over here, you can see if we comply with the minimum design actions, then the minimum moment is based on 0.05d of the axial design load. So that minimum eccentricity point shows what that value is for the column if you are approaching failure of the column. The DEC point is the decompression point, and that's the point at which the extreme fibre tension reaches zero. So in other words, the whole column is in compression. Further down we've got the balance point, and that's the point at which the tensile steel reaches yield. So this is the point at which it switches from a compression failure to a tension failure. So we're looking at the X moments here. We can also show the Y moments. So it changed slightly there. You mightn't have noticed it, but it did. And if you wanted to just look at the positive side of the X or Y moments, you can do that to get a closer look. So there's the positive Y moments. There's the positive X moments. And then you can switch to negative. But because we've got no negative moments in this particular column, you don't see any load points on that side. If you just want to look at the red curve, which is the actual, which is the capacity of the column with its actual reinforcement, you can turn off these other curves, and these other ones represent the capacity of the column that you would get if you had a steel ratio of 1%, 2%, 3%, or 4%. So we can turn those off if you want to just make the diagram a little bit clearer. You can also turn off the confinement region too. So moving across to the input part of the data, one of the key things that you need to get right is the load cases that you're designing to. And if you leave this field blank, then it will use all load cases. Otherwise, you can type in a list of load cases or click on this little button here and then select them from this list here. So this contains all of your load cases, and if we just wanted to design to the combination load cases or the ultimate load cases, we could click these blue ones here, or alternatively just click this select combinations button and then hit OK. So that puts the list of load combinations in the ultimate load case list. Biaxial bending is something you would normally consider, so that can be turned on or off. It's fairly straightforward. So for rectangular and square columns, the program just does an interaction between the equations for bending about X and bending about Y according to the code, and gives an overall biaxial capacity. And by the way, the capacity is shown at the bottom as a utilization ratio. So here you can see we've got a utilization ratio of 0.89, so the column is stressed up to 89% of its capacity, and the governing failure mode is bending about the x-axis, or that'll be combined compression and bending about the x-axis, and this is the critical load case. So in this particular case, if I turn biaxial bending off, you can see that the utilization ratio now goes down to 0.86, and we get a warning just to say that biaxial bending has been turned off and we may need to consider that. So let's turn that back on. You can do a shear check if you want to. Normally shear isn't a big problem in columns, it's mainly axial and bending, but shear can be considered if you want. As you can see, it hasn't affected the results because the shear in this case is quite small, but you may want to consider it. The minimum design actions affect the moments, and as I mentioned before, they are a function of the axial design action and the depth of the section. So you can turn that on or off, or you can use your own custom minimum design actions by clicking here and then just typing in the minimum X moments and Y moments that you want to comply with. So in this case it does have a fairly dramatic effect, because you can see here we've got 12 N36 bars in total, and if I turn that off, then we're down to 8 N36s. So it's just telling us that the axial force is quite significant and the applied moments are quite small, and then when we turn on the minimum design actions, they become a bit more significant. So one of the things that SpaceGASS does to calculate the capacity of the column is work out whether it's a short column or a slender column. And this depends on the slenderness ratio, the effective length, the brace settings, the concrete strength, and the design actions. And this is also load case specific, seeing as it depends on the design actions. So you may have a short column in some load cases and a slender column in other load cases. The classification then determines what moment magnification is applied to the moments. For short columns, there's no moment magnification unless you untick calculate and then type in some moment magnification factor that you wish to apply. But normally you would just leave that on calculate and let SpaceGASS calculate the magnification factors. Some of the things that affect the moment magnification are whether or not the column is braced and the effective length factors. So in this case we've got a column that's, let's assume it's got a pin base on it, and at the bottom, and at the top it's continuous through to the next floor column. So in that case we'd probably say it's got an effective length factor of 0.85, and you'll notice here we've got a magnification of 1.27, but as soon as I apply that 0.85 you can see it's gone down to nearly 1, so that almost eliminates all of the moment magnification. So I'll do the same with the other direction. If you've done a nonlinear analysis, then normally ticking these braced boxes here doesn't have any effect, although in some cases it may change the column from slender to short. And so if I tick this one, you can see that it has reduced the magnification factor back to 1, and that's probably because it's now classed the column as a short column, and so there's no magnification. So if you've done a nonlinear analysis, the only things that you really need to worry about in terms of moment magnification are setting the effective length factors and setting these brace options. If you've done a linear analysis, then extra magnification can be applied based on these two factors here, and they are beta D, which is essentially the ratio of dead load divided by the total load, and the lambda UC value, which is essentially the buckling load factor of the model. So by putting in 1,000, we're just assuming that there's no buckling issues at all with the model, but if you wanted to check that, you could run a frame buckling analysis, see what the buckling load factors were, and then put that in for the lambda UC value. But like I said, that only gets used if you do a linear analysis. So if you're doing a nonlinear analysis, which was what you would normally do, then neither of these values are required. Let's just quickly, to illustrate that, let's just quickly save this column, and we'll just do a linear analysis this time. So normally a linear analysis only takes a few seconds, but because this model is quite large with over 27,000 plate elements in it, it might take a bit longer than that. So a linear analysis doesn't consider any second order effects such as P delta effects, and so it generally only involves one iteration, whereas a nonlinear analysis considers second order effects such as P delta effects, and that's an iterative analysis. So for this particular model it probably increases the analysis time up to 2 or 3 minutes. Okay, so that's done. We can click OK, and now I'll just follow that up with a buckling analysis, because I just wanted to show you what effect the buckling load factor has on the moment magnification if we've done a linear analysis. So I just want to consider the combination load cases here, so I'll just click this button and they're already ticked, so we can proceed with that. So a buckling analysis is performing an eigenvalue analysis on the model, and its aim is to get two things. One is the buckling load factor for each load case, or in other words the amount by which you can factor up your load case before you reach the buckling of buckling capacity of the model. And the second thing it produces is the mode shape for each load case. So not only can you find out how much you can factor up your loads by, but you can also see how the frame is buckling, so it'll give you the actual shape, a little bit like a deflection diagram. So now that that's done, the main thing that we're looking for here is the buckling load factor of 15.09. Of course, the buckling load factor is going to be different in each load case, and this is just the lowest one that occurs in all of the load cases that we analysed for buckling. So let's just use that. We'll go out of here, back in our column, and we'll just use that and see what effect it has. So now our B to D, which is the ratio of the dead load to the total load, and I think in this case it's around about 70%. And then the buckling load factor that we just calculated was 15. And you can see that it's increased the moment magnification about Y by a little bit, but it hasn't really changed the design too much. So a buckling load factor of 15 doesn't have a great effect on the results. So I hope I haven't made that too complicated, but just to put it in a nutshell, if you do a linear analysis, then you also need to provide these two values here, and the second one is the hardest one to calculate because you need to do a buckling analysis. Whereas if you've done a nonlinear analysis, then you don't have to worry about these two values at all. So moving further down, we've got the steel range percentage, which I mentioned before, so that just controls the limits on the design. The bar size range, so you can specify the minimum and maximum sizes that you want to stay within. And then further down, the program tells you what bars it's designed. Further down the bottom, there's a couple of priorities here. So the default is set to minimum bars, but I could also change that to minimum steel. And if you just wait until that finishes designing, you can look up here and now see that it's used a larger number of smaller bars, and our steel percentage has now gone down to just above 3%. So we've saved some steel area, but we've gained a whole lot of bars. So generally speaking, it's much better just to choose minimum bars and just put up with it, finishing up with a slightly higher steel percentage, in this case 3.4%. You'll notice that as I've been changing things, such as steel percentages or whatever, it redoes the design. You can see that little rectangle that comes up in the middle, and that's because the auto option at the bottom is ticked. But if you didn't want it to happen, you can untick that, and then when I change a value that might affect the design becomes invalid because it hasn't updated itself, and you have to manually click the design button to get it back. So sometimes that's quite handy because you might be changing a whole lot of things and you're getting sick of that little pause that happens each time you make a change. The other thing is that if you change anything in here, any of the bar information that it's designed, then it turns itself into a check. So let's say I wanted to change to N32 bars and increase the count to 4 on the side. I'll just turn the auto back on. So the auto works with design or check. In this particular case, my check has failed because I've just put in reinforcements that's not adequate. But the thing I really wanted to highlight was that this button here, which is normally green, becomes red. And the reason for that is because if you've made changes to your reinforcement, you don't want to accidentally hit the design button and then lose your changes. And that gives you a message to tell you that that's what would have happened if it wasn't locked. So that's why the connection becomes, or the column becomes locked. And therefore, to revert back to design mode, you need to click that button to unlock it, and then you can redo the design. So as well as being able to change the bar counts here and the bar sizes, you can go into a bar table and you can change the individual positions, sizes, and so forth of bars if you're really keen. And similarly, you can change the tie spacing and tie size. There are also preferences that allow you to get additional control over the column design. and things like the minimum tie size, so it'll never go below 10, minimum tie spacing, minimum bar spacing, cover, and then the ranges, and the display curve percentages. So these are the other four curves that appear on the interaction diagram. There are some general settings here as well that apply to things like colors and layer names if you export to DXF and that type of thing. So another thing you can do is get a report. You can get a concise report. And it just basically summarizes your input data over here, gives you a snapshot of your reinforcement. So you can see there it's saying we need N36 bars, N12 ties at 540 centers. And then further down it gives you the detailed calculations showing the governing design actions, the critical load case, which is 101, some of the ratios of the design action to the capacity and whether they pass or fail, the loads, and these include the magnification factors, and then over on this side you get the key points on the interaction curves. And up here you can also see what the classification of the column is. So this can be either short or slender, and then the utilization ratio for each load case. So that's a concise report, and then if you get a detailed or a full report, it includes all that information plus a few more things which you can explore at your leisure. Mainly the extra things are the interaction curve points. Further down you can export your column to a DXF or DWG file and then open that in AutoCAD or some other program that understands those. And you can also save your image as an EMF file, which is an enhanced meta file, and that's slightly different to a bitmap image, because an enhanced meta file can be enlarged and without losing any clarity. So it's quite a handy format, and you can open that in lots of programs like Paint or Photoshop and produce a nice image from that. So I'll just quickly save that column, and then I'll just maybe move up and just design the same column at a higher point and just see how that compares with the one at the bottom. So we'll just change the name of this one, so level 5. And you can see using the same load cases and the same cross section, we've got much less reinforcement required, so we're down to 1%. Okay, so what I'd like to do now is switch to a different model and show how the beam design works, and then also we'll have that one's also got some columns in it, and then I'll show the concrete manager that lets you manage your beams and columns in one place. So this is another concrete building. It's got no plates in it other than the shear walls, and the lift core has been analysed as a member with a large cross section. So the only plates in this model are the shear walls, and it contains a number of beams and columns. So we'll just go ahead and design some of the beams in this one just to show you how that's done. So as in the column design module, you need to specify your cross section first. So the design module won't change your cross section, it will only specify the reinforcement. So this model has got slabs spanning two-way, and we haven't actually modelled the slabs, we've just modelled the beams as T-beams and L-beams that are supporting the slabs, and applied the slab loads as area loads to those beams. So if you wanted to look at some of those, so these are the live loads on all spans. So we've got triangular and trapezoidal loads as you'd get with a two-way action slab being supported on beams. We've got some pattern loading in here as well for the live loads. We've got some sway loads as well. And we've also set up some combination load cases that just allow us to produce some ultimate load cases that we'll use in the design of the beam, or the beams. So just quickly looking at some of the deflections. I'll scale them up again like I did with the other one. So again, they're predominantly gravity deflection or vertical deflections. There's a few sway deflections happening in that one and in some of the others. Or we could look at, say, the bending moments, turn the values on, and maybe zoom in a little bit. Sometimes it's handy to look at these in wireframe because you get a bit less congestion when you're trying to see what the diagram values are. And as you know, you can also get shear force diagrams, and I'll scale those down by just holding down the S key and rotating the mouse scroll wheel. So whenever you're scaling diagrams, it's always L for loads, D for deflections, M for moments, S for shears, A for axial, and so on, and using the mouse scroll wheel. And the reason we have a different key that you have to hold down is because you could have different diagrams displayed together. So I could have moments and shears displayed together, and if I just want to change the moment scale, I can do that independently of the shear scale. Okay, so let's have a look at the cross sections in here. So I'll switch back to rendered. So these beams here, these are the main ones taking the slab load, and I'll just double click on one of those and then have a look at it in the shape builder. So we've modeled the beam as a 600 deep beam by 350 wide, and incorporated some of the slab to create a T section. The cross sections that can be supported by the reinforced concrete beam module in Space Gas are T's, like that one. L sections, such as you'd have it on the edge of a building, and straight rectangular sections like that. So let's leave that one. So on the edges we've used an L section, so I'll just quickly show you one of those. Something like that. So again, we've used the slab as part of the cross section, and the effective width of that slab is governed by the code. So you've got to make sure you don't make that too wide, although Space Gas does adjust for that if you've exceeded the effective width of the slab when you're creating your cross sections in the beams. We've also set up some filters to enable you to isolate parts of the building more readily. So let's just have a quick look at some of those. So we've got first floor. Just going to change something here. Just turn off the graying so that it's easier to see each filter in isolation. Second floor, third floor, and so on. And the filters are defined for the floors by just specifying limits. So you can see here I've just specified y-axis limits that enclose that particular floor. So if I go back to some of the previous filters, so the first floor is at an elevation of 4 meters, so it's just between 3.9 and 4.1, and then each floor has just got a different minimum and maximum value that encloses that floor. So if we wanted to create some extra filters based on member types, we could click this button here, and let's say we just want to have a filter that's got the columns in it, just so we can isolate them if we need to. And the way you define that is ticking the section properties, and then you need to type in the section numbers that correspond to the columns. But if you don't know what they are, you can click this button, and then you can see it's quite easy just to pick out the columns in here and create your filter that way. So let's do another one with say the lift core. Choose that one. And I'll just do one more. Let's do the T-beams. So there's two different T-beams in different directions, obviously, so we'll just choose those. And one thing I forgot to do is, you'll notice with these filters the shear walls appear because they're modeled as plates. So we also need to just exclude the plates. So we can tick them on and then just hit exclude. So that's for the three that I just generated before. Okay. So now if I choose one of those new filters that I created, you can see there's our columns, lift core, and the T-beams. So it just makes it much easier to work on your model by reducing congestion. So let's go to the first floor and just design a couple of these beams here. So I'll choose this one here because it's a 3-span beam. I'll just select it by choosing these individually. And then I can right click, and I've still got the same problem as I had with the column because my screen's not big enough, but I can just scroll down to there and find it. And like the column, you'll notice that it's done a complete design based on the preferences that you've specified previously. So as I was saying before, it's one of the handy things about the Space Gas design modules in that it always gives you a design. You don't have to go putting in reinforcement to get to a starting point. It gives you that starting point and you can then work from there. So I'll just give it a title. And just moving down, you've got lists, 3 different lists of load cases in this case, rather than a single list that we had in the column. So we've got the ultimate load cases, and if I click this button, you can see that I've just used the factored up combination load cases. So they're the ones we're going to use for the strength design. Then you've got your serviceability load cases, and in this case I've just used the live load and wind load cases, and the sustained load cases. So in this case I'm just using dead load. I've included superimposed dead load in that load case as well, so it's got all the sustained loads in it. So the different load cases are dealt with differently depending on what part of the beam it's working on, whether it's deflections or strength or whatever. So you need to get those lists correct. The program can also include torsion, and that can be indirect or direct. So indirect is what you would normally get in a frame analysis, whereas direct is if you've got something like a simple beam and you've just applied a torque to it, that's when you'd specify direct. So in most cases just leave that on indirect. So before I go down to these options down here, I'll just quickly show you that the beam has been broken into zones, and if I zoom in a little bit, you can see I can select each zone and move along. And normally what it does is it'll put a zone over each support and then 3 zones in each span between the supports. And that's controlled down here. So zones per span is 5, so that includes the 3 in the span and then 1 at each support. And if you want more zones in particular spans, so for example if you've got a really long span, you may want to put some more zones in there, so you can change that if you want to. And the idea of the zones is that it does a reinforcement design in each zone, and then it looks at all the zones in the beam as a whole and tries to come up with a sensible reinforcement arrangement that suits the whole beam. So the bars are continuous all the way through, and you're not having different bar sizes in different parts of the beam. So again, like the column, you can, if I just go back to the start of it, you can turn things on and off. So if you just want to look at the longitudinal bars, We'll turn those off and just have a look at the stirrups. You'll notice the longitudinal bars extend past the end of the beam, and that's because the program has calculated all the development lengths that are required, and they can also be turned off if you just want to see where the beams end at each zone. And then you've got dimensions as well that can be turned on or off. And like the column, you can also get a 2D view. So you can see each zone labeled, the length and the grid line that it applies to in your model. So moving down, you've then got the moment envelopes shown here. And one of the things you need to be really careful about is that the program has detected your spans correctly. So in this particular case, we've got 3 spans, and they have been picked up because you can see the black triangles there that represent the supports. The program detects the spans by the jump in the shear force diagram as it goes along the beam, and that's controlled by a setting that you can change. So if I just go all the way down to the bottom here, you can see the shear step threshold of 5%, and that indicates that it's gone all the way along the beam, looked at all the shears, and if there's a step in the shear force diagram in a positive direction of more than 5% of the maximum shear in the beam, then it treats that as a support. So if you find that it's detecting supports that don't exist, or if it's not finding supports that do exist, then you need to play around with this shear step threshold until you get them correct, because otherwise your design won't be completely correct. The other things about this panel in the middle are that the zones are shown, and you can just click on any one of those to move to it. As you change to a different zone, the cross section down here shows you the reinforcement in that zone. And so in that zone you can see we've got 4N36 top bars, 3N24 bottom bars, and then in the next zone we've dropped to 2N36 top and 5N24 bottom. So it changes as you go, and you can see what those changes are. The green lines above and below the moment envelope are the capacities of the beam. So using the reinforcement at each zone, the green line tells you how strong it is in terms of bending. And that just gives you a good indication of how efficient your design is, because the closer this green line here matches your actual bending moment envelope, the closer that is, the more efficient your design is. And you can see that one tracks pretty well for positive and negative moments. In this panel down here you can see a summary of the reinforcement for the whole beam, not just for the particular zone you're in. So you can see here we've got N36 bars all the way along the top, and N24 bars all the way along the bottom. So that's what I was saying before. It's not going to change the bar size part way along the beam unless you tell it you want it to do that. And we've got a total bar weight there of 1,028 kilograms. That's controlled by the priority settings, and you can change those. At the moment it's set to minimum layers, which is usually the best one, but if I wanted to go to minimum steel, then it's redone the design, and these green curves, or these green lines, have closed in on the bending moment envelope a little bit, so it's a little bit more efficient. But the trade-off of that is that we've now got all sorts of different bar sizes. So if you look down here, you can see we've got N16s, N20s, 32s, a whole mixture of bars in the top and bottom, although we have decreased our total bar weight. So it's a more efficient design, but it's an impractical design, and so I wouldn't recommend using minimum steel unless you've really got a good reason for doing it. And then you can also choose minimum bars, which again changes the design, and it's probably not quite as efficient as the minimum layers, and you can check that by just looking here. So now we're up to 1150 kilograms of steel. So it's not quite as good. So this minimum layers is usually a fairly good one. Incidentally, in this table down here, you can also get the information of the stirrups, so you can see the different stirrup spacings as you go along the beam. So these numbers over on the right here tell you where you are positioned along the beam. You can switch to an output tab, and for the currently selected zone you get a summary of all of the design parameters. So if you wanted to check certain parts of the design, you could just have a quick look here and get the information you need fairly readily. Like with the column interaction diagrams, you can hover the mouse over any point and get the values under the mouse, and you can zoom and pan to get more detailed information. You can also switch to shears and deflections. So the deflections are, there's a number of curves shown there. The top one is the elastic deflection, and that's the same as the elastic deflection that you'll see if you look at the space gas model. Then you've got your short-term deflections. These are based on the serviceability loads using the cracked section properties. You've got your long-term deflections. These are from the sustained load cases based on the section properties adjusted for creep. And then the final curve is the total deflections. The lines below those are the limits that you may want the deflections to stay within, and you can set those down here. So you can see the line at the bottom is the L on 250 limit, and the next one up is the L on 500. So normally you'd want your total deflection to be less than L on 250, which is this one here, so it's well within that. And you'd want your incremental deflections to be within L on 500, so you can see that complies as well. So we're just looking at one load case here, but you can change to look at other load cases if you want. For the serviceability and for the sustained load cases. If you wanted to find out how it's calculated the effective section properties, you can click this button, and this just shows you the elastic moment of inertia, and then the cracked moment of inertia, and the moment of inertia adjusted for creep. So you get a fairly good feel for how they compare. So just looking at this side panel here and working our way down, you've got minimum design actions again, similar to the column program. So they're just code requirements that you need to normally comply with. The design priorities we've already covered. The zones per span, as I said, there's 3 per span and then 2 over each support, which you can change. The bar size continuity, if you untick that, just means that you may get different bar sizes in different zones. So now if you look at the reinforcement down here, you can see that we've got N36s, 32s, down to 20s as we go along the beam. So normally you would want the same bar size in all zones, so let's just tick that back on. The keep inside stirrups option is for T and L beams, where the top reinforcement will be maintained inside the stirrups, but if you want the top reinforcement to be allowed to go into the slab, then you can untick that option. You've got various reinforcement size ranges that the design will stay within, layer spacings, crack control, so if you've got beams that are more exposed because they're exterior, then you can change to exterior and you'll get slightly more stringent reinforcement requirements. And also related to crack control, you can limit the maximum allowable reinforcement stress at serviceability just by ticking that on and then specifying whatever the upper limit of that stress is. Moving further down, the next section shows the reinforcement that it's come up with in the design, and it shows that for each zone, so I can switch zones either by clicking these buttons or by just clicking in some of these diagrams here. And as I click, you can see the reinforcement is changing in here. So if you want to leave it at a design, you would just leave that section alone. But if you start making changes in there, then you're switching to a check situation. And as I showed in the column, as soon as you start making changes to the reinforcement, so I'll increase this to 3 bars, then it becomes a check. The beam gets locked so that you can't accidentally perform a design like that, and then it's really just checking what you've specified rather than designing what it thinks is the most appropriate. So to do a design, you have to unlock it and then click the design button again. So those rules apply to this whole reinforcement section. The bar anchorage, when it's calculating the development lengths at the ends, you can specify the bars to be straight or cogged or hooked. So if we put a cog, say on the top and at both ends, and then have a look in the drawing up the top here, you can see that's reflected in the image, and that obviously affects the development length of those bars. You can specify the cover, and you can also perform a moment redistribution. So just to explain, moment redistribution is linked to ductility, and ductility is achieved when the reinforcement yields prior to the crushing of the concrete if the beam is overloaded. So if your beam is over reinforced to the point that the concrete fails first, then this would obviously result in a sudden failure. And so it's desirable to have a ductile design because it avoids these types of sudden failures. For this reason, the code lets you redistribute your moments, usually by reducing the moments over the internal supports of continuous beams, with a corresponding increase in the span moments. This means that if the beam is overloaded, then plastic hinges will form over the supports, and the extra load will be taken by the bottom reinforcement in the span. So there's a number of conditions that you have to comply with before moment redistribution is allowed, and the program checks all these, but just to summarize, you need to have class N ductility bars. You can only have a maximum of 30% redistribution, so in other words, over the supports you can reduce the moments by up to 30% if the KU factor is less than or equal to 0.2, and the KU factor is the depth from the extreme compression fibre to the neutral axis divided by the total depth. And if the KU factor is greater than that, then you must redistribute by less than 30% based on what the code specifies in clause 6.2.7.2. So Space Gas lets you do it by first of all just turning it on. I'll just switch back to the moment diagram first. So just take note, we've just got the envelope there of negative and positive moments. So if I turn this on, you can see there's now a second set of curves, and they represent the redistributed moments. So it's reduced the negative moment over the column, and it's increased the positive moment in the span. So everything is adjusted, including the shears, to maintain equilibrium, and you can control whether that 30% applies at the internal supports or at all supports. So normally it would only apply at the internal supports because that's the only place you'd get plastic hinges in most situations. But if you wanted to apply it at the ends, then you can do that as well. And you can also specify whether that 30% applies at the face of the support or at the center line of the support. So generally speaking, if you're doing it at the face, then you wouldn't go the full 30%. You'd need to have something slightly less than that, because that would result in a higher redistribution at the center line. And as I was saying, Space Gas checks that all of the moment redistribution requirements are satisfied before it lets you do it. And in this case, you can see here it's stopped us due to the KU factor not being complied with. So let's just turn that off. Generally speaking, I'd say that you just need to be really careful with moment redistribution and only use it if you really know what you're doing. Just before I get off this part of this form, there's some control you get over the stirrups. You can specify the stirrup size and the spacing. You can also have multiple stirrups. So if you're designing band beams, for example, with multiple stirrup legs, you can specify those. And you can also change the inclination so they don't need to be at right angles to the direction of the beam. In all of these reinforcement sections, if you've changed one zone, so let's say I've changed the top bars to N32s, for example, I can then copy that to all the other zones by clicking that button there. Saves you having to change it in every single zone. The line down the bottom is normally green if it's passed, red if it's failed, and yellow if there's a warning. And you can see by making that change there, I've caused it to fail. So I'm getting a red line, and it's borne out by the fact that my utilization ratio is now greater than 1. So it's failed in bending and torsion. So let's go back to the design. So I'm getting a pass with a warning. So there's a warning here, just warning me about the maximum allowable stress in the tensile bars that you would probably want to investigate before you accept this design. And then over on the right hand side we get the critical load case, the critical zone, and that's the one that's highlighted there, and the utilization ratio of 0.99, and then the governing failure mode, which is bending and torsion. You can also get reports. So like with the column, you can get a concise report, or you can just get a zone specific report. So let's just have a quick look at that. So the 3 cross sections there are for critical bending, critical positive bending, the overall critical zone, and then the critical shear. So they may all coincide in one zone, or if not, you'll see multiple drawings shown there in the report. And then we get a summary of the input data, a summary of the reinforcement that it's come up for the entire beam. So you could just use this section to specify the complete reinforcement picture. Further down we start getting into the calculations, the utilization ratios for each load case, and then in the second column the zone capacity table. So these are just showing the capacities of the beam in each zone. Development lengths all the way along the beam, and the deflections, including the span on value ratio. So you can investigate those reports at your leisure. You might want to just look at the critical zone sometimes, or get a full report, although that does include quite a bit of data. Beam preferences, there's quite a few in this case. So things like maximum layers, clearances, distances, whether torsion is included by default, the fire resistance period, default number of zones and layer spacings, bar anchorage. So if you change any of these, they won't change the current beam. They'll just become the default for all of your new beams. The development length multiplier depends on things like, if you've got epoxy coated bars, then you'd use a multiplier of 1.5, or if you've got lightweight concrete, for example, or if your elements have been built with slip forms, then you might use 1.3. Otherwise you'd probably just use 1. These settings here are quite handy, because if you wanted to design at the face of the column as opposed to a distance away from the face of the column, then you can set some of these values here. So for example, the shear is designed taken as a value at the face of the column, but if you want to move away from that, you can specify that and then just give it a distance of say 150 millimeters or whatever you specify. And similarly with the moments, you can comply with clause 623 if you want to alter where the maximum negative moment location is as the beam meets the column. Further down, you've got the parameters that all affect the calculation of deflections, so you can specify those to your requirements. And then at the bottom we've got, first of all, these parameters here are all AS3600 specific, and then further down we've got equivalent parameters that are IS456 specific. So if you go higher up, all of these values are general purpose that apply to all codes. If you ever set some of these and you're not sure what they should have been at the beginning, you can just click the reset button to put them back to the factory defaults. And then, like I showed with the column program, you can produce drawings. So we could produce a DXF or a DWG. Let's produce a DWG. Or we could produce an image file, which like I mentioned before, is an EMF file or an enhanced meta file. So now that we've produced that DWG, let's just go and see if we can open it in the DWG viewer. So I'll just find that file. There it is. And then zoom the extents. And so you can see for each zone, the program produces a cross-section and a summary of the reinforcement in that cross-section. And you also get a longitudinal section showing the grid lines and the reinforcement required. So let's save that beam, and then I'll just quickly do another couple of beams. Let's say this one. And instead of using the menu, I'll click here like I did with the column and choose beam. So check the spans again. So this time it's got it correctly again. So 2 spans. I haven't found a case where it doesn't get it correctly, but I'm just alerting you to the fact that you just need to keep that in the back of your mind. And so everything else applies similarly to the 3-span beam that I did the first time. So let's give this one a title. And we'll accept that one. I'll do one of these longitudinal beams. Now these are quite lightly loaded because the slabs are this is the short direction of the slabs, and so they're not going to attract too much load, but we'll just quickly do one. So it's 5 spans, and you can see there the capacity green lines are way above the actual moment envelope, indicating that the beam is not working to full capacity, but that's what you'd expect in those beams that aren't attracting much load. So we'll accept that one. I better give it a title. And I'll just do one more. This is a T-beam in that direction as well. So I'm taking the easy way out by just accepting the design results, but obviously if you need to change the reinforcement to your specifications, then you'd modify some of these settings to get it to exactly how you want. Click OK. And we could just keep going through the structure, designing them that way. Now I just want to design a couple of columns quickly so that I can show you the concrete manager and how it can be used to manage your beams and columns in one place. So let's do that column. And just for speed, I'm going to just accept that one. I'll just give it a title first. My naming convention's not great here, I know that, but I'm just trying to differentiate between them for when I get into the concrete manager. And maybe I'll just do another one, say this one. And let's say that's enough for the time we've got. So the next thing I wanted to show you is the concrete manager, and that's accessible through here. And that lists all of the beams and columns that you've got in your model. So in this table at the bottom, you've got the two columns that I hurriedly put in at the end, and you've got your beams over here. So I can go into any of those just by double clicking on that line. So I'm back in the editor, and now I can make whatever changes I want, and then click OK, and that will update it in here. You can also scroll through them just by clicking on them and seeing over here the critical zone and the reinforcement in that critical zone. And similarly with columns, I could just scroll through them this way, or double click on one to open the editor for that column. So it's quite a handy tool. Lets you see all of your beams and columns in one place and perform various operations on them. So let's say I had reanalyzed my model. Normally you would only reanalyze it after you've made a change to it, but let's just say I've done that. So I'm doing a nonlinear analysis, and then that would erase all of the beam and column design results because the design actions could have changed. So then the idea of the concrete management tool is that you can redo all those designs just in one place. So first of all, you'd tick the beams and columns, or if you just wanted to redesign the beams, you'd tick that, or columns, you'd tick that, or both. You can select which ones you want to design. You can choose your load cases, as we did inside each individual one before. And if you're happy with all that, you can just do a design, click the design check button, and that will go through and redo each one. So any changes you've made to your reinforcement or anything inside the beam and column editors will be maintained. All it's doing is just redesigning what you previously had. And so now we're back with results again. The line at the bottom here is a bit like the one in the editor, where it's green if it's passed, red if it's failed, and yellow if it's passed with a warning. And you also get the critical load case and the utilization ratio for whichever item you've clicked on. Another useful thing about the table is that I can use it to export the data to other programs. So if I just select all of the beams and columns in this table and then right click, you can see I can export that to other programs, and similarly I can import back into the table from Excel or Access. You can also create combined reports of beams and columns and subsets of them if you just list them individually, and you can set up whichever parts of the reports that you want to include. So once you've ticked all those boxes, you can generate the report, and then there's a table a tree on the left that allows you to go to individual parts of the report. So that's for beams, this is for columns. Or you can just scroll through them manually to get to wherever you want to go. And the management tool also gives you access to the preferences for both beams and columns. So that's the end of the training part of the session. So I hope you enjoyed it, and thanks for your attention.